Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I will introduce you to SPSS. Inside this video, we will review what SPSS is and what it's used for, the two main windows in SPSS, including the data editor and the output viewer, and the menu options in SPSS. By the end of this video, you will have a basic understanding of the SPSS environment. Let's begin. SPSS, or the Statistical Package for the Social Sciences, is a statistical software program that can analyze your data in three basic ways. First, it allows you to describe your data using descriptive statistics. Examples of this include frequencies, mean, minimum, max, and standard deviation. It also allows you to examine the relationship between variables in your data. Examples of statistical techniques to explore relationships include correlation analysis, regression, and factor analysis. Finally, SPSS enables you to compare groups using t-test, analysis of variance, and non-parametric statistics. Now let's look at the two major windows in SPSS. When you first open up SPSS, you will see what is called the data editor. Okay? The data editor is where you create variables, you enter data, and you carry out statistical functions. All right? Now, you will notice that there are two tabs in the data editor: the Data View tab and the Variable View tab. The first tab is the Data View. This is used for entering data as well as viewing data in the data editor. The rows represent the individual cases, and the individual cases can be people, businesses, states, countries, what have you. Okay? The columns represent the particular variables in your data file. Okay, so let me give you an example. In the world95.sav file that comes with SPSS, at least the later versions of SPSS, the first variable, because these are all variables, the first variable is the country. Okay, and each case is represented as an individual or separate country. Now, for Afghanistan, the predominant religion is Muslim. The average life expectancy for the females is 44. The average life expectancy for males is 45. Okay? The second tab, as I mentioned before, is the variable view. The variable view is used to create and define various characteristics of variables. Here, the row represents individual variables, and the columns represent the specific characteristics of those variables. Okay, so let's look at our world95.sav file as an example. Now, row 1 is the country variable, row 2 is religion, row 3 is average female life expectancy. Column 1 is the name, column 2 is the type, column 3 is the width of that particular variable. I'd like to quickly review the menus in SPSS. Now, I say quickly because I'm going to review each of these, or most of these, in far more detail in upcoming video tutorials. Okay, so let's begin with the file menu. Now, the file menu contains the standard options that you would see in other Windows programs, such as save, print, open, new, and so on and so forth. Okay. The edit menu is another standard menu where you can cut, copy, and paste. Also, you can edit SPSS preferences by clicking on the options button here. View, here is where you can indicate if you want to see grid lines or display value labels. Now, right now grid lines is not on, but if I click that, then you can see, or should be able to see, the grid lines. So under data, This menu allows us to make changes to the data editor. You can insert variables, you can insert cases, split the file, and select cases. Again, we will discuss these in more detail in future video tutorials. We have the transform menu, which is used when you want to manipulate one of your variables in some way. The analyze menu is where all of these statistical procedures are located. We will go into what each of these statistical options do when I show you how to run the various statistical analyses in other video tutorials. Okay. Now the graph menu is used when you only want to produce graphs without running any analysis. And again, I will show you how to do that in another video tutorial. Utilities is used when you have production jobs or you want to obtain information about the variables in your file. Okay. Now add-ons is a menu that is used when you have or when you've purchased a analytical module that doesn't come with SPSS. Now all of these modules are sold separately, so if you purchase an additional module for SPSS, you would actually run it under the add-ons menu. Now the Windows menu allows you to switch between windows, as you pretty much know, and the help obviously is help. Okay? The second major window is the output viewer. This is simply where the results of any analysis appear, including charts built with the chart builder. So if we go to the world95.sav file and run frequencies on average female life expectancy, we will see what is produced in the output viewer. Okay, so let's go to world95.sav. We run analyze, descriptive statistics, and then frequency. We then select the particular variable or variables we'd like to see frequencies for. And then we make sure that display frequency tables is checked. We go to statistics. We select the measures of central tendency that we're interested in. We click continue. Next we go to charts. We select bar chart, click continue, and then click OK. As you can see, the output viewer is broken into two parts. The left side contains an outline or menu pane which gives you a full list of all the analysis you've performed. You can use this side to quickly navigate your way around your output. So if you want to see the bar chart, you want to see the frequency table or the summary table, you can just simply click on one of those. Okay? On the right side of the viewer are the results of your analysis, which can include tables, charts, and graphs. The first thing we see is the syntax statement. This is a written record of the executed command. Next, we have the name and path of the active data set, which is world95.sav. Following that, we have the summary table, which contains the total number of cases in each variable along with the mean, median, and mode. So in this example, there are 109 cases in the average female life expectancy variable. The mean is 70.16, the median is 74, and the mode is 75. Okay? Next we have the frequency table, which tells you the number of times each value occurs for this variable and the corresponding total percentage that this number represents. Okay? So for example, there are 4 women with an age of 58. These 4 women represent a total of 3.7% of the total. Now, you always want to look at the valid percent because the percent column takes into account all values, including missing. Okay? Whereas the valid percent excludes the missing values and calculates the percentage based on cases that have data. Okay? And then finally over here you have the cumulative percentage, which is simply the additive percentage from the smallest value to the largest value. And this is always going to equal 100%. Okay, and then finally we have the bar chart, which gives you a graphical representation of the value frequencies for this variable. Okay, so basically this is a graphical representation of the frequencies column here. Okay, so as you notice, the numbers increase as the age increase, the number of frequencies increase, and we see that here. Okay. SPSS is a statistical software program that allows you to analyze your data in three basic ways. You can describe your data using descriptive statistics. You can examine the relationships between your data using correlations and multiple regressions, or you can compare groups using t-test, analysis of variance, or non-parametric test. Additionally, there are two main windows in SPSS, the output viewer and the data editor, which consists of a data view and the variable view. If you have any questions whatsoever about this video or any other video, please submit your questions to Jacob Mays at jacob@spssvideotutor.com. This has been an SPSS video tutorial from spssvideotutor.com. Thank you for watching. Much success with SPSS. Welcome to this video tutorial from spssvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to input data manually into SPSS. There are 4 steps to manually input data into SPSS. The first step is to number your questionnaires. If you have 50 questionnaires, each questionnaire should have its own unique number from 1 to 50. The reason why this is important is because you need to be able to include an ID number in your SPSS file so that you can connect your respondent data to a questionnaire. So let's say you're checking your data using frequencies and you see that you've made a mistake on one of your variables. Okay, you've input the wrong number. If you don't have an ID number, then it's very difficult for you to go back and find the correct questionnaire so that you can input the correct number. Okay? The next step is to create a code book. The third step is to define your variables in SPSS. And the final step is input your data. Let's go into steps 2, 3, and 4 in more detail. A code book is a blank questionnaire, meaning it has no responses, where you define how you're going to code your questions and your answers in SPSS. Okay? So let's go to our code book and I will demonstrate what this is. Now, so I've created a code book for this sample questionnaire. And the code book tells you a couple of different things. Okay, so for the first question, which is age, we have Q1. So this is going to be our variable name. Okay, so for each one of these, we determine what our variable name is going to be. Now, the second thing that the code book tells us is how we're going to code individual responses. Okay, so for age, if someone says they're 18 to 24, we're going to code them as a 1. If someone says that they're 25 to 29, under Q1, we're going to give them a 2. 30 to 34 in the Q1, we're going to give them a 3. 35 and older, a 4. Okay? Now let me say this before I go any further. Do not type in text in SPSS. So for example, don't type in 18-24 or female, F-E-M-A-L-E. SPSS is a quantitative analytic tool. That means you need to convert everything you can to numbers. And that's what the code book process is for. Okay? Now, continuing on. So our second question is gender. And we're going to code that Q2, question 2. Okay? And under question 2, we're going to code females as 1 and males as 2. Now, single select categorical. This means that Your answers are categorical and you can only select one. Okay, same thing for age. Your answers are categorical and you can only select one. So it's a single select categorical variable. Okay, it's a multiple choice question where you select only one option and it's a categorical variable. Same thing for number 2. Number 3, again, it's a single select categorical variable. So level of education is going to be coded or as Q3 as the variable name, and some high school education is going to be coded as 1, high school diploma 2, all the way up to 6, which is other. Now, you want to code your lowest values with low numbers and your highest values with high numbers. Okay, so the lowest ages get a 1, the higher ages get a 4, which is the highest value. Now for gender, there's no high or low value, so the codes can be arbitrary. All right, same thing for level of education. The low levels of education get low scores, the high levels of education get high scores. All right, now for number 4, our continuous rating scale, we're going to code this as Q4 for our variable name, and we're just going to plug in the value that they give us. Okay, so if they give us a 10, then we're simply going to type 10 into the SPSS data file. All right, for number 5, it's a little different. This is what you call a multiple select categorical variable. Again, your answers are categorical, but you can select multiple responses. All right. It says below select the topics that you covered in your statistics class. So the way we code multiple selects of this nature is as follows. If they select it or check it, it gets a 1. If they don't select it, it gets a 0. Okay, so these are dichotomously coded variables. It's either they had the class or they had the topic or they didn't. Okay, same thing for dependent sample test. If they had this in their class, it gets a 1. If they didn't, it gets a 0. Now, because each one of these individual responses is getting a code, it has to be labeled as its own variable. Okay, so independent sample t-test gets a code, so therefore it is going to be coded Q5A under question 5, right? So it's question 5A. Dependent sample test Q5B. Bivariate correlation Q5C. Multiple regression Q5D. These are all options under question number 5, and the letters just indicate their order in the question. All right, same thing for number 6. You have a situation where each of the components receives a rating. Okay, because each one of these gets a rating, then it has to be coded as its own variable. Okay, under question 6. So it's Q6A, Q6B, Q6C. This will make more sense when I start coding this in SPSS. Once we have coded our questionnaire and created a code book, we go to our SPSS data file. Okay, and we start out with a blank slate and we go to variable view. Our first variable is going to be ID. Okay, our second variable is going to be question 1, which is age. So under name, we go Q1, click enter. Decimals, just change it to 0. Label, and we're just going to label this as age. Okay, and then under values, the values are here. So 1 equals 18 to 24. 2 equals 25 to 29. 3 equals 30 to 34. Click add, and then 4 equals 35 or older. We click add, and then we click OK, and then you click save. Okay, Every time you add a new variable, you want to click save. Now, so then we go to the second one, which is gender. So that's going to be Q2. Okay? It's numeric. And then we're going to type in gender. And then values 1 for female, 2 for male. Click OK. And then save. Okay? And then you do the same thing for Q3. Okay? Now, for number 4, Q4, again, click enter, and then this one is simply how challenging is stats class, and then the values, there's no values because this is a continuous variable, right? So there's no values that need to go in here, okay? And then for number 5, okay, we see here that we have 4 variables. So it's Q5A, and then we're going to type in independent sample t-test, and then Q5B is going to be dependent sample t-test. Okay, so a 0 is not selected and a 1 is selected. Click OK, and then we can just hit copy and then paste. So as you can see, I've added the 4 responses under question 5 and have labeled them accordingly. Okay? And then you go on to question 6. And again, this one has 3 options. So it's Q6A, and then we've got handouts. Now, since this one is a continuous variable, there are no values. Okay? So Q6B, enter, text, books, and then Q6C, videos. Okay, so now that you have set up your data file, now you can begin entering data. Okay, so the third step is entering data. Okay, so the first step was creating a code book. The second step was setting up your data file, and now the third step is going to actually input data. So now we go to a sample survey that has the respondent ID of number 1. Okay? So originally we were on variable view, now we go to data view, and this is respondent 1. Okay? So look what SPSS did. So when we put in our variables, the variables are along the top. So each column is a variable. Okay? Now the rows are respondents. Okay? So the respondent number 1 is ID 1. Okay? And then for age, they were 25 to 29. So we know that if someone's 25 to 29, they get a 2. Okay? So we put a 2 there. And then for question 2, they are female, so they get a 1. And then for question 3, they have an advanced degree, so that's number 5. And for question 4, they rated level of challenge a 4, so we're going to put 4 there. And then for question 5A, they did not select this because it's not bold, so they get a 0, okay, for question 5A. For question 5B, they get a 1, okay, because I've actually darkened this or made it bold, okay. Question 5C, they selected bivariate correlation, so they get a 1 there. Question 5D, multiple regression, they get a 1 there, okay. Now, for question 6A through C, this respondent number 1 gave a 9. For textbooks, they gave an 8. And then for videos, they gave an 8. Okay? So our first respondent's data has been entered. Now you know how to input data manually in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to import a text file into SPSS. Let's first look at the text file we're going to import into SPSS. The name of this file is text.txt. As you can see, the file is comma delimited, meaning each data point is separated by a comma. Additionally, we see that each line represents one case. A case can be an individual, country, or anything else that has data associated with it. When you're importing data into SPSS, it's important to know whether or not the first row contains variable names and on which line of the text file your data begins. SPSS will ask you these questions during the import procedure. In this example, there are no variable names in this text file, and the data begins on line 1, the very top of the file. Now let's actually begin the process of importing text data into SPSS. First, make sure that the text file is closed. SPSS cannot import data from an open file. Next, open up the SPSS program. Go to File, Open, Data, change the file type to text. Select the file that you're interested in and click Open. The SPSS text import wizard box opens and you will see the path of the document and a small window showing a few lines of data. There's the path, and obviously here's the data. At the top of the dialog box, you will be asked if your text file matches a predefined format. Just select No. Click Next. In this example, we will select delimited because we saw earlier that our text file was comma delimited. If your data is organized into fixed width columns, select fixed width. Since there are no variable names in this document, we're going to select No here. Click Next. Here you select on which line your data begins. That's number 1. If each line represents one case, as it does in our example, we make sure that that's selected. And in the area that asks us how many cases to import, we want to import all cases. Click Next. You may notice that the data in the window appears to be very fragmented. For example, University of Alaska at Fairbanks should be one term under one variable, but it is now broken up across several variables. If we uncheck space, then we see that the data is more orderly. Click Next. Next, you will be asked if you want to change the specifications of the variables. Just skip this. It's better to do this in SPSS. Click Next and then Finished. You will now see the data from the text file in SPSS. Now, one of the things that you will notice is that there are stars under some of the variables. So, for example, variable 5 has stars where there are missing values. If we go to variable view, we see that variable 5 is a string variable. If we change this to numeric, click OK, and go back to the data view, we see that the stars are no longer there and are replaced by periods, which represent system missing values. The last step is to save your data as an SPSS file. Click Save, and you're done. We now have a new SPSS data file titled test.sav. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to import an Excel file into SPSS. Let's first look at the Excel file we are going to import into SPSS. The name of this file is datafile_01.xls. We see that this file contains variable names in the first row along the top of each column. It's important to know if your Excel file contains variable names because SPSS will inquire about this during the import procedure. We also see that the first cell containing content is A1 and the last cell is BM93. This is important to note because during the import procedure, SPSS will give you a range from which it is pulling data, and you want to make sure that the range includes all of your data. In this case, the range should be A1:BM93. Finally, we see that the other two worksheets contain no data. Worksheet 2 is empty, and Worksheet 3 is empty. Now let's actually begin the process of importing Excel data into SPSS. First, make sure that the Excel file is closed. SPSS cannot import data from an open Excel file. Next, open up the SPSS program. Go to File, Open, Data. Go down to the Files type and change this to Excel. Then go to the folder or location on your computer where your Excel file is located. Select the file, click Open. Next, you are going to see a dialog box. And this dialog box contains the path of your data file. You will also see a checkbox that asks if you want to read variable names from the first row of data. In this case, we will say yes, because we saw that our data file contains variable names across the top of the file. If the Excel file does not contain variable names in the first row, then uncheck this box. Next, SPSS tells us from which worksheet and cell ranges it is pulling the data. If data was contained on multiple worksheets, we would be able to select different choices on the pull-down menu. However, since there was only one sheet that contained data, we only have one choice here. The range shown includes all of our data because our data went from A1 to BM94, so this is good. If you wanted to shorten or broaden the range, we would do so using the range text box. We would use the same format that we use in Excel, where you have the letter and the number of the first range separated by a colon, then the letter and the number of the ending range point, the same way you see here. The maximum width of string columns is fine. Click OK, and you will see your data in Excel. You will see that SPSS has imported the variable names from your Excel file into SPSS. Additionally, in some instances, SPSS has attempted to create variable labels for your data based on the variable names. Next, you want to check to see if all your data has been imported into SPSS. The final step is to save your data in SPSS, and then you will have completed the import process. So we simply just type in the name here, and then we click save, and we're done. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to convert string variables to numeric variables in SPSS. Okay, in this demonstration I have created a mock data file that has one string variable, and the name of that variable is string. Now if we go to variable view, we see that it is a string variable. The width is 8, nominal, 8 columns, so on and so forth. Okay, so we see that our string values are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Now, so we want to convert this variable into a numeric variable and retain the values in each cell. So what we do is we go to transform, we go to recode into different variables. We see that string, our variable string, is here. We move that over. We are going to name our new output variable numeric, and we'll change that. And then we go under old and new values. Okay, now we want to check convert numeric strings to numbers. Okay, and then we're just going to put a value here. So 1 is going to equal 1, and then we click add. We don't have to do all of them, you only have to do one. You click continue, then you click OK, and then when you go back to your data file, the new variable that you created, numeric, will be on the far right hand side of your data file. So if you have a lot of variables, you will have to go all the way to the right hand side to see this new variable. Also, all of your string values have been converted to numeric values. So if we go over to variable view, we see that the new variable named numeric is a numeric variable. It has a width of 8 and 2 decimal places, and it is now a scaled measure instead of nominal. Okay? Now you know how to convert string values that are numbers into numeric values. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to create box plots in SPSS. In this demonstration, I will create a box plot of occupational prestige scores. The first step is to go up to Graphs, down to Legacy Dialogues, and then over to Box Plot. In the second step, we see that we have a few options. The first option is the simple box plot. If we want to create a box plot of a continuous variable, we select summaries of separate variables. Okay? If we want to create a box plot of a continuous variable separated into groups of a categorical variable, we select simple and then summaries for groups and cases. Okay? So let's first run summaries of separate variables. Okay? We go to define. We look for our continuous variable and we move it into the box represents area. We go to options, make sure that exclude cases listwise is selected, click continue, and then click OK. So in our case summary box, we see the number and percentage of valid responses for the occupational prestige score. And we also see the number and percentage of cases that we're missing. And this is all based on the total of respondents in the data file, which is 1,517. Okay, here we have a box that represents the interquartile range. Okay, 50% of your scores are contained within this box. The line going through the box is the median value. Okay, these lines protruding out of the top and the bottom of the box are called the whiskers. Okay, they extend out to the highest value in the particular variable and to the lowest value of the particular variable. Okay, now out here are what SPSS considers the outliers. Okay, so an outlier is considered anything that is 1.5 box lengths from either the top edge or the bottom edge of the box. Okay, now the outliers will be denoted by a circle and then numbers surrounding the circle. These numbers are actually case numbers. So the respondent that is 199 in the data file has an outlier score. Okay, so if we go back to our data view, and this is the 199th case, and we go over to prestige, they have a value of 86, which is considered an outlier when you look at all of the other values. Okay? Now, if we want to run a single continuous variable grouped by a categorical variable, we go to Graphs, Legacy Dialogues, then down to Box Plot. Make sure that Simple is selected. And instead of summaries of separate variables, we click summaries of groups of cases. We click Define. We select our continuous variable and move it into the variables box. And then we select a categorical variable and move it into the category axis box. So for this example, we're going to use sex, and we're going to move it over to the categories axis box. Select options. Everything is fine here. because exclude cases listwise is okay. We click OK. Now, for the box plot that produces a summary of groups, we see that occupational prestige is broken out by male and female. Okay? So again, we see the interquartile range, which represents 50%. We see the median value here, the median value here. And one of the things that we notice is that all of the outliers in occupational prestige scores are associated with the males. Okay? So again, when we ran the simple box plot and selected summaries of groups of cases, we got a box plot that was broken out by the category gender. When we simply ran the box plot by summaries of separate variables, we produced a single box plot for our variable. So those are the major differences when running those two different box plots. Now you know how to create a box plot in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching, and much success with SPSS.
In this clip, we will discuss frequencies and descriptives. Frequencies and descriptives can be used for any numeric variable. However, only frequencies can be used for string variables. For this clip, we will use the new drug data that is already opened. We would like to find the percentage of female patients and the percentage of patients that received the placebo treatment. From any active window, you can select Analyze, Descriptive Statistics, and Frequencies. The source variable list on the left contains all variables that can be analyzed by this procedure. Note that since this is a frequency procedure, you have both string and numeric variables available. Scale variables are represented by a ruler, and numeric ordinal variables are represented by a histogram. Numeric nominal variables are represented by a three-colored dot symbol, and string variables are represented by the same three-colored dot symbol but with a letter A. The target variable list is on the right, and the variables in this list are the variables that will be used for analysis. For this, we will select treatment and gender. With the Statistics button, I can choose statistics that I want to display, such as mean, median, mode, standard deviation, minimum, and maximum, and click Continue. With the Charts button, I will choose the bar chart, since these are categorical variables, and click Continue. With the Format button, I can change the order of the variables and how some output is displayed, either all variables in a single pivot table or each variable in a separate pivot table. But you should keep in mind that formats will only change if descriptive statistics are requested. Now click Continue. Observe that frequency tables are displayed by default, and these are the tables we are interested in looking at, so we will make sure these are displayed. When I am ready, I can choose Paste and run the procedure later, or click OK and run the procedure now. I will click OK. Here is the frequency procedure displayed in the output window. You can see that no statistics are displayed for gender because it is a string variable. If we look at the frequency tables, you will see that 44% of patients received the placebo treatment and 52% of patients for the study were female. Now, let's go back to the data editor window. We would like to look at the simple descriptive statistics like mean and standard deviation for the variables before and after blood pressure. To run this procedure, go to the Analyze menu, Descriptive Statistics, and since we only want simple descriptive statistics, we will use the descriptives procedure. But if you want more statistics, like percentiles and median, you should use the frequency procedure. Now select descriptives. You might note that you only have numeric variables in your source variable list. This is because only numeric variables can be analyzed with this procedure. Let us select the before and after blood pressure. Let's go to the Options sub-dialog box. By default, descriptives give mean, standard deviation, minimum, and maximum. And by default, the order of the variables is to display them in the order they appear in your data file. These are the settings I want, so click Continue and OK. And here are the descriptives I asked for. The mean for the before blood pressure is 98.3, and the mean for after blood pressure is 88.598. And as you can see, this means that the blood pressure went down in this study. Now you know how to obtain the frequencies on numeric or string variables, and how to obtain the descriptives on numeric variables.
Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to create bar charts in SPSS. In step 1, you go to Graphs, you go to Legacy Dialogs, and then Bar. In step 2, we have a few options. The first option is a simple bar chart. If we want to create a bar chart of groups within a continuous, categorical, or nominal variable, we choose Summaries for Groups of Cases here. So we click Simple, Summaries of Groups of Cases, and then Define. So for this example, we are going to choose Region, and we see that we have a number of options up here. The bar can represent number of cases, cumulative N, percent of cases, cumulative percent, and then there are other options here as well. But we're going to choose percent of cases because that's the most popular. If you want to add titles to your bar chart, you can do that by clicking on titles and then typing in the name of the title here as well as footnotes. But we're just going to click OK. And we see that the name of our variable is at the bottom. The category names of the variable are along the very bottom of the box. And along the left side are the percentage of respondents who live in each region. Okay. Now, if we want to add data values to these bar charts, we double click the right mouse, okay, and then we left click on the bar chart, okay, and then we go down to Show Data Labels. Here we have the option of changing the number of decimal places. We can actually change this to 0 by going under normal format. If we go back to data value labels, we can determine the position of the labels. If we want them at the very top, we can select that here. We want them in the middle, we can select that here under custom, or the very bottom, but we're just going to leave it with automatic. Click apply and then close, and then X bar out, and we have data value labels on our graph. Okay. If we wanted to create a bar graph of 2 or more variables side by side, we would choose summaries of separate variables. Okay, so simple, summaries of separate variables, and then define. This is commonly used for paired sample t-test, where you create a bar chart of the mean scores for each of the 2 comparison variables. Okay, in the bars represent box, you must have at least 2 continuous variables, as these are generally mean scores. So we're going to select SIBS and age, and then click OK. The average number of brothers and sisters of respondents is 3.9, and the average age of respondents was 45.5. Okay? Now, the final choice just gives you the value for each case within a variable. So if you had 30 cases for a particular variable, you would have 30 bars that would represent the individual scores or values for that variable. We're going to skip this because it's not used that often. Okay? Now, the second option is a clustered bar chart. If we want a single variable grouped by another variable, we choose summaries for groups of cases. Okay? An example of this would be gender and region, where you would have 2 bars, one for male and one for female, within each regional group. So we put region in the category, and then we put sex in the define clusters by. Okay, so the define clusters by is always going to be your bar chart, and the category axis is always going to be the variable that contains the bar charts. So let's select % of cases and then OK. We see that the Northeast region has a greater percentage of males and females compared to the Southeast and the West. Okay. Finally, if we wanted a bar chart of multiple variables grouped together by a single categorical variable, we choose summaries of separate variables. So for example, we could have age and education level by gender, where for each gender we would have 2 bars, one for average age and one for average level of education. So we select age, education level, and then gender or sex. Now remember, continuous variables are used in the bars represents box. Okay, you have titles and options as always, and click OK. So we see here that for males, the average age is 44.2 compared to 46.6 for females, and the highest year of school completed on average is 13.2 compared to 12.6 for females. Stacked is the same as clustered, except that the bars are stacked on top of one another instead of side by side. Okay, so just to revisit, if we go back to the very top, we had a simple graph where we had summaries for groups of cases, where we had one variable and bar charts for the groups within that variable. Okay. Then we had another simple graph, but instead of categories within a variable, we had individual variables. So this was number of brothers and sisters, and this was age of respondents. And we had the mean age of respondents and the mean number of brothers and sisters. Okay? Now, for the clustered bar chart, we had summaries for groups of cases where we had one variable grouped within another variable. So we had gender grouped within each region. So we had males and females in the Northeast region, males and females in the Southeast region, and males and females in the West region. And then finally, we had clustered bar charts where we were looking at summaries of separate variables. Okay? So we had individual variables displayed within one variable. So within gender, we had mean age and the mean highest year of school completed. Okay? So now you know how to generate bar charts in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to create and interpret histograms in SPSS. In this demonstration, I will create a histogram of occupational prestige scores, a continuous variable in our data file. Occupational prestige scores reflect the level of social status and income associated with a person's job. So a doctor would have a high occupational prestige score, while a street sweeper would have a low occupational prestige score. Okay, so the first step is to go to Graph, Legacy Dialogues, then down to Histogram. Then what we do is we find the continuous variable that we want to create a histogram for. In this case, it's occupational prestige, and we move it over to variable. Now we can also click this to display a normal curve over our data. Next, we can create a title for our histogram. So we can say occupational prestige scores and click continue. Now, if you desire to create separate histograms for different groups, say males and females, you can put an additional variable in the panel by section. You choose the row if you want the two histograms on top of one another, and you choose columns if you want the histograms side by side. Okay? So we're going to leave that blank for now, and we're just going to click OK. When we look at our histogram, the bottom numbers represent the individual scores, and the numbers along the side represent the frequency of those scores. In this example, the scores are normally distributed, meaning the data looks like a symmetrical bell-shaped curve where scores with the highest frequency are in the middle and scores with the lowest frequencies are at the extremes. So they can be the extreme left and the extreme right. You may have instances where your variables are not normally distributed. So they could be positively skewed, where you have the data skewing down this way towards the right, or you could have the data skewing down towards the left, which would be negatively skewed. Or a third option would be for all of your scores within a variable to sort of just be in a rectangular shape where they all sort of distribute equally across all of the scores. In any of these cases, there are data transformations that you can do to repair normality of your variables. I will cover this in another video tutorial titled Repairing Normality. Now, finally, if you want to copy your chart or your graph or bar chart or whatever into Word, what you simply do is you right click, you hit copy, you go to Word, you open your Word document. Now your cursor is going to be at the top, so what you do is you just hit enter twice so that you can create some space. You right click again and you hit paste, and there is your histogram. You can do this for bar charts, you can do this for any chart that you create in SPSS. Now, if you want to type text below your chart, you see that your cursor is going to be at the very bottom. You just hit enter, and then you can type text at the very bottom, or you can type text at the very top. That's why we hit enter twice, to create some spacing. Okay, now you know how to generate a histogram in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been an SPSS video tutorial from SPSSvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret an independent samples t-test. In this demonstration, I will use a data file called the 1991 U.S. General Social Survey. You can find it in the SPSS sample data folder. This data set contains over 1,500 respondents from the 1991 General Social Survey. It includes statistics on age, gender, marital status, attitudes about health and work, and so on. Let's begin by examining if there is a difference in education level between males and females in this data set. Okay, so the first thing you do is you go to Analyze, you go down to Compare Means, and you go to Independent Sample t-test. Next, you take your dependent variable, which is education, and you move it to the Test Variables box. Next, you find your independent variable for gender, which is sex, and you move it down into the Group Variable box. Now, here you will have to define the group. If you don't remember what the particular groups are for your grouping variable, then you right-click your mouse, hit Variable Information, and you say that 1 equals males and 2 equals females. Okay, so you go to define groups, so 1 equals males and 2 equals females. Okay, hit continue and then OK. In the group statistics box, we see the number of cases or respondents for males and the number of cases or respondents for females. We also see the mean number of years of school completed for males and the mean number of years of school completed for females. Additionally, we have the standard deviation for both groups, males and females, and the standard error of the mean. The second table is the independent samples t-test. The first part of the table gives us the result of Levene's test of equality of variances. Okay, one of the assumptions of the t-test is homogeneity of variance. If your significance value is equal to or greater than 0.05, the assumption of homogeneity of variance is met, and you use the first line in the table to determine if there are significant differences between the two groups. If it is less than 0.05, then you use the second line, which is equal variance is not assumed. Okay? The first line is equal variance is assumed, and the second one is equal variance is not assumed. So in this case, it's less than 0.05, so we use the second line. Okay? Now, to find out if there is a significant difference between the two groups, we refer to the column labeled significant two-tailed, which appears under the section labeled t-test for equality of variances. Okay, so this is what we're looking for right here. If the value in the significance two-tailed column is less than 0.05, then there is a significant difference in the mean scores of your dependent variable. So for this example, under equal variances not assumed, the two-tailed significance level is less than 0.05. So therefore we can say that males have completed significantly more years of school than females, with the average number of years of school completed for males being 13.3 and the average number of years of school completed for females being 12.63. In summary, an independent samples t-test tells you whether there are significant differences in the mean scores of two different groups of people or conditions. You need two variables to run a t-test. One is a categorical variable that has no more than two groups and serves as your independent variable. The other is a continuous variable that serves as your dependent variable. If you have any questions, please submit them to Jacob Mays at jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a one-sample t-test. In this example, we have a classroom of 18 students and the number of absences for all 18 students last year. We want to see if there is a significant difference in the average number of absences in this classroom compared to the average number of absences in the entire state. Okay, so the average number of absences in the entire state is 15. So in order to determine this, we go to Analyze, we go to Compare Means, and then we go to One Sample T-Test. Okay, we move the variable of interest, the test variable, into the test variables box, and then we put our test value here in this box. So since our test value is 15, the value that we're comparing our average to, then we put it there. We go to Options, make sure that's on 95, exclude cases pairwise, and then we click Continue, and then we click OK. Now, the first table that we see in the output file is the one sample statistics that contains the mean, standard deviation, and the standard error of the mean, okay, along with the number of respondents in the analysis. So we know that the mean number of absences in the classroom is 29.44, okay? Then we go down to the one samples test table. Our test value is 15. Our t-value is 5.077, or once you write your results, it would become 5.10, okay, because that you would round it off to the second decimal point. Your degrees of freedom is 17, and your mean difference is 14.44. Now, the most important thing here is the significance level. Because this is less than 0.05, that means that there is a significant difference between the mean number of absences in the classroom and the test value. Okay, so basically you would state that the mean number of absences in the classroom is significantly greater than the mean number of absences in the state. Okay, now you know how to perform a one sample t-test in SPSS. If you have any questions, please submit them to Jacob at SPSSvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a dependent samples t-test. In this demonstration, I will use a data file called fearofstats.sav. It contains data from a fictitious study to test the effectiveness of an intervention program designed to reduce fear of statistics. Each student was given a fear of statistics test before the intervention program and the same fear of statistics test after the intervention program. Let's begin by examining if there is a significant difference in the fear of statistics mean scores before and after the intervention program. So the first thing that we do is we go to Analyze, we go to Compare Means, then we go to Paired Samples t-test. We see that our variables are on the left and we have a paired variables box on the right. So we take the two variables that we're interested in comparing and move them over to the paired variables box. So the first variable is FOST1, which is fear of statistics time 1, which is the pretest, and FOST2, which is fear of statistics time 2, which is the post-test. Okay, we go to Options. We make sure that this is set to 95%. We also want to make sure that under missing values, exclude cases analysis by analysis is selected. We click Continue, and then we click OK. In the output viewer, we first see the paired sample statistics table. SPSS gives you the mean, the number of cases in each group, or the sample size, the standard deviation for each group, and the standard error of the mean in each of the groups. Okay. SPSS also gives us the Pearson correlation between the two conditions. When repeated measures are used, it is possible that the experimental conditions will correlate because the data in each condition come from the same people, and so there could be some constancy in their responses. So we see here in these results that it's a very strong correlation at 0.862, and this correlation is significant. And we say it's a very strong correlation because the correlation's coefficients range from -1 all the way up to +1, where the absolute value of 1 represents a perfect correlation. So this is a very, very strong positive correlation. The third table that we want to look at is the paired samples test. In this table, we have the mean differences between scores, which is simply this minus this. We have the standard deviation of the differences between the means and the standard error of the differences between the participant scores in each of the conditions. We also have the confidence interval, the lower and upper level confidence interval, and the t value, the degrees of freedom, and the two-tailed significance level. To find out if there is a significant difference between the two test scores, we look at the column labeled significant two-tailed. If the value in the significant two-tailed column is less than 0.05, then there is a significant difference in the mean scores of the two tests. So to interpret the data, we go back up to the paired sample statistics box and we look at the mean scores for each of the 2 test periods. We see that the fear scores for the pretest on average were 40.17. We see that the mean scores after the intervention were 37.50. So there was a significant decrease in fear of statistics scores after the intervention. Okay, so basically the results indicate that the intervention program appears to reduce fear of statistics. Now remember, you can never say that the intervention caused the reduction in fear in statistics because there are so many other factors that could explain that. Okay, so now you know how to run a dependent samples t-test. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been an SPSS video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a one-way analysis of variance. In this demonstration, I will use a data file called the 1991 U.S. General Social Survey. You can find it in the SPSS sample data folder. Let's begin by examining if there is a difference in occupational prestige among respondents from 3 regions. In this example, occupational prestige is the dependent variable and region is the independent variable. Region has 3 factors: northeast, southeast, and west. Just to clarify, occupational prestige scores reflect the level of social status and income associated with a person's job. So a doctor would have a high occupational prestige score, while a street sweeper would have a low occupational prestige score. The first step is to go to Analyze, then Compare Means, and then down to One-Way ANOVA. Next, we go and we find occupational prestige score, and we move it into the dependents list. Following this, we go to Region, and we move the region variable, which is our independent variable, into the factor box. Okay. Next, we go to Options, and we select Descriptives, Homogeneity of Variance, and Brown-Forsyth. Okay. For missing values, make sure Exclude Cases Analysis by Analysis is selected, then click Continue. Next, we go to Post Hoc, and we select Tukey under Equal Variances Assumed, and then under Equal Variances Not Assumed, we select Games-Howell. We click Continue, and then click OK. Now let's review the results of the ANOVA in the SPSS output window. Okay, the first thing we see always is our syntax that was actually executed for this analysis. Okay. Second, we see the descriptives table, and this gives us information about each group, including the number of cases in each group, the mean scores of each group, and the standard deviation, standard error, and so on and so forth. Okay. The second table that we see is labeled the test of homogeneity of variance. And this displays Levine's test for homogeneity of variance. This tests whether the variances in scores is the same for each of the 3 regional groups. All this means is that the absolute difference between the mean and raw scores of each group need to be generally the same across all groups. If the significance value is 0.05 or greater, then you have not violated the assumption of homogeneity of variance. If this value were less than 0.05, then the assumption of homogeneity of variance is violated, and you will need to use the table labeled robust test of equality of means instead of the ANOVA table. In the ANOVA table, the main thing we are interested in is the significance value, right? So this right here. If the significance value is less than 0.05, then there is a significant difference somewhere among the mean scores of the independent variable region. Okay? It's important to note that this does not tell us which groups are different from each other. For that, we have to look at the table labeled multiple comparisons. Okay? Now, if the assumption around homogeneity of variance was violated, meaning if this were less than 0.05, then we would use this table instead of the ANOVA table. We only look at the multiple comparison table if we find the significance value is less than 0.05 for the ANOVA or the robust test of equality of means. If the variances are equal, we use Tukey's HSD. If they are not equal, we use the Games-Howell test. Okay, so we look down the column labeled mean differences and look for any asterisks next to the values listed. Okay, so we have one here between the West and the Southeast. Okay, wherever you see an asterisk, this means that the two groups being compared are significantly different from one another at the p less than 0.05 level. Therefore, we see that the respondents in the Southeast region have significantly different occupational prestige scores than those in the West. Okay? So if we go back up to the top, the mean occupational prestige score for the West is 43.82, and for the East, it's 41.58. Therefore, based on the results of the ANOVA, the West has significantly higher occupational prestige scores than the East. If you have any questions, please submit them to Jacob Mays at jacob@spssvideotutor.com. This has been an SPSS video tutorial from spssvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from spssvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a one-way analysis of variance. In this demonstration, I will use a data file called the 1991 U.S. General Social Survey. You can find it in the SPSS sample data folder. Let's begin by examining if there is a difference in occupational prestige among respondents from three regions. In this example, occupational prestige is the dependent variable, and region is the independent variable. Region has three factors: Northeast, Southeast, and West. Just to clarify, occupational prestige scores reflect the level of social status and income associated with a person's job. So a doctor would have a high occupational prestige score, while a street sweeper would have a low occupational prestige score. The first step is to go to Analyze, then Compare Means, and then down to One-Way ANOVA. Next, we go and we find occupational prestige score, and we move it into the dependence list. Following this, we go to region, and we move the region variable, which is our independent variable, into the factor box. Okay. Next, we go to options, and we select descriptives, homogeneity of variance, and Brown-Forsyth. Okay. For missing values, Make sure Exclude Cases Analysis by Analysis is selected, then click Continue. Next we go to Post Hoc and we select Tukey under Equal Variances Assumed, and then under Equal Variances Not Assumed we select Games Howell. We click Continue and then click OK. Now let's review the results of the ANOVA in the SPSS output window. Okay, the first thing we see always is our syntax that was actually executed for this analysis. Okay. Second, we see the descriptives table. And this gives us information about each group, including the number of cases in each group, the mean scores of each group, and the standard deviation, standard error, and so on and so forth. Okay? The second table that we see is labeled the test of homogeneity of variance. And this displays Levene's test for homogeneity of variance. This tests whether the variances in scores is the same for each of the three regional groups. All this means is that the absolute difference between the mean and raw scores of each group need to be generally the same across all groups. If the significance value is 0.05 or greater, then you have not violated the assumption of homogeneity of variance. If this value were less than 0.05, then the assumption of homogeneity of variance is violated, and you will need to use the table labeled Robust Test of Equality of Means instead of the ANOVA table. In the ANOVA table, the main thing we are interested in is the significance value, right? So this right here. If the significance value is less than 0.05, then there is a significant difference somewhere among the mean scores of the independent variable region. Okay? It's important to note that this does not tell us which groups are different from each other. For that, we have to look at the table labeled multiple comparisons. Okay? Now, if the assumption around homogeneity of variance was violated, meaning if this were less than 0.05, then we would use this table instead of the ANOVA table. We only look at the multiple comparison table if we find the significance value is less than 0.05 for the ANOVA or the robust test of equality of means. If the variances are equal, we use Tukey's HSD. If they are not equal, we use the Games Howell test. Okay, so we look down the column labeled mean differences and look for any asterisks next to the values listed. Okay, so we have one here between the west and the southeast. Okay, wherever you see an asterisk, this means that the two groups being compared are significantly different from one another at the p less than 0.05 level. Therefore, we see that the respondents in the southeast region have significantly different occupational prestige scores than those in the west. Okay? So if we go back up to the top, the mean occupational prestige score for the west is 43.82, and for the east, it's 41.58. Therefore, based on the results of the ANOVA, the West has significantly higher occupational prestige scores than the East. If you have any questions, please submit them to Jacob Mays at jacob@spssvideotutor.com. This has been an SPSS video tutorial from spssvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from spssvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret Friedman's ANOVA. In this demonstration, we will examine if there is a change in depression scores across 3 different time periods. pre-intervention, post-intervention, and follow-up. So the first thing that we do is we go to Analyze, Non-Parametrics Test, then K-Related Samples. Next, what we do is we select the variables that represent depression. Okay? So in your case, what you would do is you would move the variables that you are analyzing or comparing into the test variables box. So in this case, for us, it's depression scores. So it's depression time 1, depression time 2, and depression time 3. Okay? So this is the pre-intervention, post-intervention, and follow-up. We make sure that Friedman is selected. We go to statistics and we make sure that quartiles are selected. Click continue and then click OK. The first thing that we see our output is descriptives table. In descriptives table we have the number of cases for each time period. We have the 25th percentile rank time period, the 50th percentile rank, and the 65th percentile rank. Okay? You will use median scores or the 50th percentile rank interpreting and writing your result. Okay? Now, next table that we see is the rank table. Okay? The rank gives us the mean rank on depression scores each of the 3 time periods. Okay? The higher the mean rank, the higher score on the continuous variable. So, in this case, the higher the mean rank, the higher depression scores. Okay, so depression 1 had highest depression scores. Depression time 2 had the second, and depression time had the lowest. Next, we select our continuous dependent variable, total self-esteem, and move it into the test variables list. We then take our independent categorical variable, which is age group 3, and move it into the grouping variable box. Click on Define Groups and type in the first value of your categorical variable in the minimum box and the highest value in the maximum box. If you don't remember what the minimum and maximum values are, you can right-click on the variable, click on Variable Information, and see what the min and max values are. So they're 1 and 3. So we go to Define, we type a 1 in the minimum box and 3 in the maximum box, and click Continue. And then OK. We need the median values for each group when reporting the results, whether they are significant or not. So we go to Analyze, Compare Means, and then Means. Okay, so then we take our dependent variable, which is total self-esteem, and move it into the dependents list box. Then we take our independent variable, which is age group 3, and move it into the independents list box. We go to Options. We remove mean and standard deviation, and then we replace it with median. We click Continue, and then OK. Okay, so the first table that we see is the case processing summary table. This just tells you the number of cases that are included and the number and percentage of cases that were excluded. And then we get to the so when we look at the Kruskal-Wallis test, the first table that we see is the ranks table. The ranks table gives us the number of cases for each age group and the mean rank on total self-esteem for each group. Okay? The higher the mean rank, the higher the score on the continuous variable. So here, the lowest mean rank was on the lowest mean rank on total self-esteem was among the 18 to 29 group, and the highest mean rank was with the 45 plus group. So the 45 plus group had the highest scores on the total self-esteem measure, and the 18 to 29 had the lowest self-esteem scores on the total self-esteem measure. Now, the test statistic gives us the chi-square, the degrees of freedom, and the significance level. The test statistic give 3, 2, 1. The test statistics table gives us the chi-square, the degrees of freedom, and the significance level. If the significance level is less than 0.05, which it is, then there is a statistically significant difference in total self-esteem scores across the three groups. Now, since the results only indicate that there is a statistically significant difference somewhere among the three groups, we need to run post hoc comparisons using the Mann-Whitney test. This test will tell us which age groups are significantly different from one another. Now, the next part is very important. When performing the Mann-Whitney test for post hoc testing only, you must divide 0.05, which is your significance criteria, by the number of post hoc comparison tests you are making. Okay? So, Since we are going to be comparing the 30 to 44 group versus the 44 plus group and the 18 to 29 group versus the 30 to 44 group, we would have to divide 0.05 by 2, okay? Because there are two comparisons that we're making, two post hoc comparisons, okay? That means that our new significance level would be 0.025, not 0.05, okay? So when we run the Mann-Whitney test for post hoc comparisons, if the significant difference between the groups is greater than 0.025, then it is not significant. Now you know how to perform and interpret a Kruskal-Wallis test. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a chi-square test for independence. In this demonstration, we will examine if there is a relationship between taking part in a rehabilitation program for first-time criminals and second arrest. Participation in the rehabilitation program is our first categorical variable, and it contains two categories. Yes, you participated in the rehabilitation program, and no, you did not participate in the rehabilitation program. Second arrest is our second categorical variable. It also contains two categories. Yes, you were arrested a second time. No, you were not arrested a second time. Because each of these variables has two categories, this is considered a 2x2 design. In order to perform the chi-square test of independence, we go to Analyze, we go to Descriptives, then we go to Crosstabs. Next, we select our first categorical variable, which is rehab, and we move it into the rows box. Then we select our second categorical variable, which is second arrest, arrest 2, and we put that in the columns box. We then go to statistics, select chi-square and phi and Kramer's V, and then we click continue. Then we click on the cells button. We check expected, observed should be checked. Then we select rows, columns, and total percentages. We click continue, and then if you're pasting it to your syntax file, you click paste. If not, you click OK. Now, the first table that we see is the case processing summary table. Okay, this tells us the number of respondents that are included in our analysis and the number of missing cases. So we have 1,000 people who have been included in this analysis, and there are no missing cases. The second table is our crosstabs table. Each cell contains the count for that cell, expected count, row percentage, column percentage, and percent of total of all cells. Okay? So for example, in the first cell, we see that there are 210 people who did not partake in the rehabilitation program and who were not arrested a second time. The expected number for this cell is 243.9. The row percent is 30.4, so this corresponds with the row. So 30.4% of respondents who did not participate in the rehabilitation program were arrested, and 69.6% were arrested who did not participate in the rehabilitation program. The next number is the column percent, which is 59.5. So 59.5% of respondents were not arrested a second time and did not participate in the rehabilitation program, and 40.5 were not arrested and did participate in the rehabilitation program. Okay? And the final number is the total percent. So this number, this number, this number, and this number in the total all equal 100. Okay? Now, if we go down to the chi-square test table, the first thing we want to look at are the footnotes. Okay? Here you check to see if you have violated the assumption of the chi-square. The assumption is that the minimum expected cell frequency for each cell should be 5 or greater. Or, put another way, at least 80% of the cells have expected frequencies of 5 or more. Okay? So, if this number is greater than 20%, this assumption has been violated. So, if it's greater than 20%, you need to either gather more data or, if possible, collapse your cells into larger groups using the recode procedure to create higher counts in each cell. Okay? Now, once you've determined that you have not violated the assumption, if you have a 2x2 design, which we have here, you look at the data in the second row labeled continuity correction. Okay? If either of your variables has 3 or more categories, then you look at the first row labeled Pearson chi-square. Okay? So, for example, if we replaced the variable participation in the rehabilitation program with region, which has 3 categories, north, south, and west, we would look at the Pearson chi-square. Okay? But in our case, since it's a 2x2 design, we're going to look at the continuity correction. Now, in either case, if the value of the asymptotic significance two-sided is less than 0.05, then there is a statistically significant association between the two variables. Since our significance value is below 0.05, this means that the proportion of rehabilitation participants who were arrested a second time is significantly different than the proportion of non-rehabilitation participants who were arrested a second time. So in order to determine which group actually performed better, those who participated in the rehabilitation program and those who did not participate in the rehabilitation program, we go back to the crosstabs table and we look at the percent within rehabilitated. So always look at the third one from the top. Okay? We see that 30.4% of those who didn't participate in the rehabilitation program were not arrested a second time versus 69.6% that were arrested a second time. Then we compare that to those who did participate in the rehabilitation program. 46.3% were not arrested a second time and 53.7% were arrested a second time. So, since we know from the chi-squared that these numbers are significantly different, then that means that those who did not participate in the rehabilitation program were more likely to be arrested a second time than those who did participate in the rehabilitation program. Okay? Now, finally, we go to the last table. Okay? This output table contains statistical tests that measure the effect size or strength of the association. Like the correlation coefficient R, they range from 0 to 1, where higher values indicate a stronger relationship between variables. Okay? You want to use the phi statistic when you have a 2 by 2 design. Okay? You use Kramer's V if either one of your categorical variables has 3 or more categories. Okay? Now you know how to perform and interpret a chi-square test of independence. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from spssvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from spssvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a chi-square test for goodness of fit. In this demonstration, we want to test whether the proportion of smokers in our data file is equivalent to the proportion of smokers reported from another study. This other study reported that 20% of its respondents were smokers. So, in order to compare the proportions of smokers in our study to the proportion of smokers in the other study, we first go up to Analyze, down to Non-Parametric Test, and then chi-square. In step 2, we select the categorical variable of interest and move it into the test variable list box. So in this case, it's smoke. Okay? In step 3, we go down to expected values. And because we're comparing it to another study that indicated that the proportion of smokers was 20%, we click on values. And since our first value is yes, meaning smoker, and that corresponds with 20%, then we put 0.20 in this box. We click add, and for the remaining value, we type in 0.8 and we click add. Now, the first value always corresponds to the first value in your data file. So if the first value is a 1, this number corresponds with 1. If the second value is a 2, it corresponds with a 2. If you have a third value, which is 3, then that corresponds, the third value, the number that would go here would be associated with the 3. Now, if all of your categories proportions were expected to be equal, then you would select all categories equal. Meaning that if our 2 smoker groups, 1 meaning smoker, 2 meaning non-smoker, if we expected them both to be 50%, then we would select all categories equal. Additionally, if we had a category or a variable that had 4 categories and we expected them to be all equal, then each category, each of the 4 groups would be 25%, and we would just highlight all categories. Okay, but in this case, we have 2 categories, and the comparison we're making is with another study that said that 20% were smokers, 0.20, and conversely, 80% have to be non-smokers. Now remember, these values in this box always have to add up to 1. No matter how many categories you have, they always have to add up to 1. Okay? So finally, we click OK, and we come to our output window. In the first table, you have observed and expected frequencies. The observed frequency is the actual number of cases in your data file. So there are 85 respondents who say they smoke, and there are 351 respondents who say they do not smoke. Okay? The expected frequency is the number of cases that should be in each group based on the proportions that we specified in SPSS previously. So based on the 20% proportion that we put into SPSS, our expected N for this cell, or the expected number of smokers, should be 87.2, and the expected number of non-smokers should be 34.8. Now let's look at the second table. The test statistics table indicates whether there is a significant difference between the observed and the expected frequencies. In this table, we see that the value for chi-square is 0.069. We see that the degrees of freedom is 1, and we see that the significance level of the chi-square value is 0.792. Because the significance level of the chi-square value is greater than 0.05, this indicates that there is not a significant difference between the observed and expected proportions. Now you know how to perform a chi-square test for goodness of fit. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today we will cover correlation analysis. In this video, you will learn how to perform and interpret a bivariate correlation in SPSS. Now let's look at how we actually run a correlation in SPSS. In this demonstration, I will use a data file called world95.sav. You can see it there. You can find it in the SPSS sample data folder. This data set has information on 109 countries, from Afghanistan all the way to Zambia. It includes statistics on population, population density, religion, life expectancy, and so on and so forth. Let's begin by examining the relationship between female life expectancy and 4 other variables, namely literacy, gross domestic product, daily calorie intake, and birth rate per 1,000. The first step is to click on Analyze, then go down to Correlate, and then click on Bivariate. In step 2, select the variables you want to analyze and move them into the variables box. So let's select female life expectancy. Let's see, literacy, gross domestic product, daily calorie intake, and birth rate per 1,000. Under correlation coefficients, the Pearson correlation coefficient is selected by default. This is used for quantitative variables that are normally distributed. If you know that your data is not normally distributed, then you should choose Spearman. Under Test of Significance, make sure that Two-Tailed is selected, and also make sure that Flag for Significant Correlations is also selected. Now we go over to Options over here on the right. Click on that. Under Missing Values, make sure that Exclude Cases Pairwise is selected. Hit Continue, then click OK. You will notice that the results display in what we call an output window. The results of all of your analysis show up in this window. The first thing we see is the syntax statement up here. This is a written record of the command just executed. Next, you will see the name of the analysis run, which is correlation, followed by the name and path of the data file used, right here. And then below that, we have the correlation matrix. Notice that the 5 variables we have chosen are displayed across the top and along the sides of the correlation matrix. In each box, we have the correlation of the variable in the row and the variable in the column. So for example, the variable in the row is gross domestic product, and then the variable in the column is average female life expectancy. So this is the box that corresponds with that. So then the next one, daily caloric intake, and average family life expectancy is the box that corresponds with that. Where you see the ones going along the diagonal, that's each variable correlated with itself. So that's birth rate correlated with birth rate per 1,000, daily calorie intake correlated with daily calorie intake, and of course these are all perfect correlations. Also, the matrix is symmetrical along the diagonal. So the 0.865 correlation here is the same 0.865 correlation here. It's people who read, average female life expectancy, and then people who read over here, an average female life expectancy. Same thing over here, where you have gross domestic product by average female life expectancy is 0.642, and gross domestic product by female life expectancy is 0.642. Remember, correlations go from -1 to +1, where the absolute value determines the strength of the relationship and the sign in front of the number determines the direction of the relationship. In each cell, you will see 3 numbers. The first number is the Pearson-R correlation, or the Pearson product moment correlation coefficient, better known as simply R. In this example, it is 0.865, which is pretty high and a very strong positive correlation. This indicates that as literacy increases, so too does female life expectancy. The second number is the significance level, or the p-value. If this number is less than 0.05, then we say that the correlation is considered statistically significant. All this really means is that we are extremely confident that an R of 0.865 did not occur by chance. The final number is the number of cases in this analysis. In this instance, the value represents the number of countries that had data for both average female life expectancy and literacy rate. Okay? The key takeaway here is that all of these correlations are statistically significant. Okay? So if you look, you notice that all of the R's have stars after them, which means that they are statistically significant, of course, excluding the perfect correlations going down the diagonal. So for example, birth rate per 1,000, as the birth rate decreases, average female life expectancy increases. This is an inverse relationship. As birth rate decreases, the percentage of people in a country who read increases. As birth rate decreases, the gross domestic product of a country increases. As birth rate decreases, daily caloric intake increases, and so on and so forth. We will use these same variables in the multiple regression tutorial, where we look at the association of all of these variables collectively. In summary, a correlation is used to describe the strength and direction of the linear relationship between 2 variables. Pearson's correlation coefficient, or R, ranges from -1 to 1. The sign indicates whether there is a positive relationship, meaning as one variable increases, so too does the other, or a negative relationship, meaning as one variable increases, the other variable decreases. The size of the absolute value indicates the strength of the relationship, where 0 equals no relationship and 1 indicates a perfect relationship, where the value of one variable can be exactly determined by knowing the value of the other. If you have any questions related to this video, statistics, research, SPSS in general, please contact Jacob at jacob@spssvideotutor.com. This has been an SPSS video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a partial correlation in SPSS. In this demonstration, after controlling for social desirability, we want to explore the relationship between a person's perceived control over their internal states and total perceived stress. Social desirability is the tendency to convey oneself in a positive light on self-report scales. Perceived control of internal states is the degree to which we feel we can control our emotions, thoughts, and physical reactions. To show themselves more positively, some people inflate their positive scores and deflate their negative scores in surveys. So, we want to remove this bias from our correlation results. The first step is to go to Analyze, Correlate, and then Partial. Next, we select the two variables we want to analyze and move them into the variables box. So in this case, they are total perceived stress and total perceived control. In step 3, we click on the variable we want to control for. In this case, it's T Marlowe, which is our measure of social desirability. Step 4, we go to Options, and we make sure that Exclude Cases Pairwise is checked. And in Statistics, we make sure that Zero Order Correlations is checked. This produces a matrix of simple correlations in the output file between all variables, including the control variable. Next, click Continue, Two-tailed, Display Actual Significance Level that needs to be selected, and then click OK. You will notice that the correlation table is broken up into two sections. The top half of the table is the normal Pearson correlation matrix between all variables without controlling for the confounding variable, social desirability. That is why this is labeled None under Control Variables. Now, we see that across the top are all the variables and across the side are all the variables and their correlation coefficients. So, of course, total perceived stress has a correlation coefficient of 1, and the correlation coefficient for perceived stress and total perceived control is negative 0.582. The correlation between total social desirability is negative 0.232. So, basically, as total perceived stress increases, total perceived control scores decrease. Same thing for total social desirability. As total perceived scores increase, total social desirability decreases. Okay? Now, the bottom half of the table is the partial correlation when controlling for social desirability. Therefore, this is labeled total social desirability. The resulting partial correlation is negative 0.52. So, when we control for total social desirability, we see that the correlation is -5.2. So if we compare the two sets of correlation coefficients, we see there is only a small decrease in the strength of the correlation from -0.582 to -0.552. This suggests that the observed relationship between perceived control and perceived stress is not due to the influence of social desirability. Now you know how to perform and interpret a partial correlation in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a multiple regression. In this demonstration, I will use a data file called world95.sav. This dataset has information on 109 countries from Afghanistan to Zambia. It includes statistics on population, population density, religion, and so on. In this example, we want to know how well do literacy, gross domestic product, daily calorie intake, and birth rate predict female life expectancy. The first step in running a linear regression is to go up to Analyze, Regression, Linear. Next, we move female life expectancy, which is our dependent variable, into the dependent box. After that, we move our independent variables into the independent box. So we have literacy, gross domestic product, calorie intake, daily calorie intake, and birth rate per 1,000. Okay. Next, we need to open the statistics sub-dialog box. Estimates and model fit are already pre-selected by default. Estimates gives us regression coefficients, and model fit gives us statistics including R-squared. So they're very important. We want to check for collinearity problems, so we need to select collinearity diagnostics. And then we click Continue. Next, we click Plots. Here we want to select histogram and normal probability plot to compare the distributions of the standardized residuals to a normal distribution. These last plots are very important because having a normal distribution is a key assumption of the linear regression. Click Continue and then click OK. Here you can see that all four variables were entered using the enter method and no variables were removed. Okay? The model summary shows us the prediction power of this model. We have an adjusted R-squared of 0.822, which basically means that our model explains 82.2% of the variance in female life expectancy. So the prediction power of this model is pretty high. The ANOVA table tells us the overall significance of this model. The F value and the P value tell us that these variables are jointly significant in predicting female life expectancy. Basically, this means that the model is significantly better at predicting the outcome of life expectancy than using the average for female life expectancy as the best guess. To look at the p-values of each variable, we have to look at the coefficients pivot table below. Here we see that the p-values of literacy, daily caloric intake, and birth rate per 1,000 indicate that these are all significant variables in the model. Next, we look at the VIF, which is the variance inflation factor, to assess multicollinearity. Generally, a value higher than 10 indicates a multicollinearity problem. We see that all 4 variables have acceptable VIF values. Finally, if we look at the charts, we can see that the histogram of our residuals looks fairly symmetrical, and the PP plots show a good agreement with the ideal line. Thus, the residuals are approximately normally distributed. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching, and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a logistic regression in SPSS. In this example, we will explore how well 5 variables predict whether people report having problems sleeping. The 5 predictive variables in this analysis are age, gender, hours of sleep per weeknight, problems getting to sleep, and problems staying asleep. Now, before you begin your logistic regression, you want to make sure that your dichotomous variables are coded 0 and 1, or dummy coded, where 0 is the absence of the characteristic, or no, and 1 is the presence of the characteristic, or yes. Okay? This will make interpreting your results much easier. Okay, so for example, we have trouble staying asleep. We said 0 was no and 1 was yes. For trouble falling asleep, again, 0 is no and 1 is yes. And problem sleeping, 0 is no and 1 is yes. Okay? For gender, we did 0 female and 1 male. Okay? Now, obviously, that doesn't apply for gender because there is no presence of the attribute. Okay, so, but still, you need to code your dichotomous variables 0 and 1. All right? Now, to begin, we go to Analyze, we go to Regression, we go down to Binary Logistic. The first thing that we do is we move our dependent or outcome variable into the dependent box. Okay, so problem sleeping is our dependent variable. Okay, next we move our independent or predictor variables into the covariates box. So for this example, it's going to be sex, hours of sleep per weeknight, problem staying asleep, and problem falling asleep. Okay? Now, under method, we're going to make sure that this is enter. And then next, if we have categorical variables as our independent variables, we go to categorical. Okay? And what we want to do here is we want to move our categorical variables, whether they're dichotomous or multiple categories, into the categorical covariates box. So we're going to move sex, problems staying asleep, and problems falling asleep. Okay? Then what you're going to do is you're going to make sure that contrast is at indicator. Okay? You can change this if your professor recommends a particular contrast, but we're just going to leave it as indicator. And we're going to change our reference to first. Okay, so we're going to change our reference to first for each one of these. And what this means is this: our reference comparison is going to be the first category. So for gender, it's going to be females. So we're going to highlight that and click change. For trouble sleeping, the first category is 0, obviously. So, and that's no trouble sleeping. So we're going to click change. And then trouble falling asleep, again, we click change. and we should have first after all of our variables. Next, we go to continue, we go to options, and then we want to select classification plots, Hosmer-Lemeshow goodness of fit, case-wise listing of residuals, and we also want to select the confidence interval for the exponentiated standard coefficients or the odds ratio. And then we click continue, and then we click OK. Okay, so the first table that we see is the case processing summary table. This tells us the number of cases included in the analysis, the number of cases that were missing from the analysis, and the total number of cases in the entire sample. And it also gives us the associated percentages. You want to make sure that if you have a high number of missing cases, that you go back and look at your data to ensure that there are no significant errors. All right. The next group of tables are the dependent variable encoding table and the categorical variables coding table. This shows you how your dichotomous variables have been coded. Okay. Whenever you run a logistic regression, your dichotomous variables always have to be coded 0 and 1. Now, we did this earlier on in our data file. However, if you begin this analysis and you have not coded your dichotomous variables as 0 and 1, SPSS will do it for you. Okay? So it's very important to pay attention to these tables because they're critical in helping you interpret your results. Okay? The next section, labeled Block 0, contains the predictive results of your analysis without any independent variables included. Okay? This is sometimes called the constant-only model or the reduced model. This will serve as the baseline for comparing our full model that includes all of the independent or predictive variables. All right? Now, the classification table shows us that the Block 0 model correctly classified 58.9% of the cases. Now, to get 58.9%, the baseline model selected the category of the dependent variable with the largest number of cases and assumed that everyone is in that category. Okay? So, since there were more people that stated they didn't have a problem sleeping, 172, compared to those who said yes, which was 120, SPSS guessed that all people did not have a problem sleeping, and as you can see, it was right 58.9% of the time. Now we want to see if adding the independent variables improves our prediction accuracy. Now, this just gives you some basic statistics about the constant-only model, not important. This just tells you the variables not included in the equation, not important. Now we go to Block 1. It contains the full model with all of our independent variables. The omnibus test of model coefficients compares how well this model performs compared to the baseline model, Block 0. Specifically, it shows the results of the chi-square test of goodness of fit. If the significance value or the p-value in the row labeled model is less than 0.05, then the Block 1 model is a significantly better predictor than the Block 0 model. So we see that in this case, our model is a significantly better predictor than the Block 0 model. Okay? Now, the model summary table tells us the amount of variation in the dependent variable explained by the model. So in this case, 27.6% to 37.2% of the variability is explained by our model. Okay? Now, These are sort of pseudo R squares. And the reason they're sort of referred to as pseudo R squares is because they don't follow the same assumptions as the general linear model regressions. Okay? The Hosmer-Lemmerschau is another goodness of fit test, and it tells us if our model is a significantly better predictor than the block zero model. Okay? Now, significant values greater than 0.05 mean that the model is a better predictor than the block zero model. Okay? Now, this is contrary to what we typically see where p-values less than 0.05 are significantly different. So for Hosmer-Lemmerschau, it's the opposite. If your p-value is greater than 0.05, then there's a significant difference. All right? So this mirrors the results of our omnibus test above. Now, we go down to a very important table, which is the variables in the equations table. This tells us which of our independent or predictor variables make a significant contribution to our model. So we have the B, which you would see in a regression. You have the standard error of the B. You have the wall test, which is conducted to determine if the predictor variables make a significant contribution to the model. You have the degrees of freedom, and then you have the significance value of the wall test. Okay? If this is less than 0.05, then that means that the independent or predictor variable makes a significant contribution to the model. So we see that hours of sleep per week, trouble staying asleep, and trouble falling asleep all make a significant contribution to the model. Next, we see the column labeled exponentiated B, or the exponentiated standard coefficient. And this basically tells us the odds ratio for each of the independent variables. Okay, so said another way, the odds ratio is the change in the odds resulting from a unit change in a predictor. Okay, now scores between 0 and 1 indicate an inverse relationship between the dependent variable and the predictor or independent variable. Okay, so think of in terms of less likely. All right, scores above 1 indicate that there is a positive relationship between the predictor and the outcome variable. All right, so think in terms of more likely. All right, so the way that you would interpret the data below is as follows. So let's start with hours of sleep per week. Now, for every 1 hour of sleep per week you get, again, it's a unit change in 1 unit is 1 hour. For every 1 hour of sleep per week you get, you are less likely to report having a sleep problem. Now, you're less likely because, again, 0.643 is less than 1. It's between 0 and 1. So it's always less likely. Now, if we go to trouble staying asleep, that is a dichotomous variable. So 0 was coded as no problem staying asleep, and 1 was coded as problem staying asleep. So since the unit change is 1, then we speak in terms of people with problems staying asleep. So the way that you would interpret this is as follows. People who have problems staying asleep are 7 times more likely to report that they have a sleep problem than those who do not report problems staying asleep. Okay? Now we go to trouble falling asleep. All right? Again, since it's dichotomous, you're going to use the category that refers to 1 or the unit 1. Okay? So people who report that they have a problem falling asleep are 2 times more likely to report that they have a sleep problem than those who do not report problems falling asleep. Okay? Now, when we go down to the last table, this indicates the cases in your sample where the model does not fit well at all. Okay? It displays cases that have a z residual value above 2.0. Okay? Now, if your z residual values are greater than 2.5 or less than negative 2.5, the specific cases should be examined for possible errors. All right? Now you know how to perform and interpret a logistic regression. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a Spearman rank order correlation. In this demonstration, we will examine the relationship between total self-mastery, total optimism, and total perceived stress. So we go to Analyze, Correlate, Bivariate. So we select the variables that we want to analyze and move them into the variables box. So let's select total self-mastery, total optimism, and total perceived stress. Okay, then we select Spearman and uncheck Pearson because Pearson is the default. We make sure it says two-tailed significance unless for some reason you only want to look at one-tailed. Make sure that flag significant correlations is selected. Go to options and make sure that exclude cases pairwise is selected. Click continue and then click OK. Now, one thing you may notice about the output table of the correlation matrix is that it looks exactly the same as the Pearson correlation matrix table. Okay, the layout of the output and the way you interpret the data is exactly the same as the Pearson correlation. So, if we look under total optimism, the number in the first row is Spearman's rank order correlation coefficient. Okay, the number in the second row is the two-tailed significance value, or the p-value. All right. The third row displays the number of cases included in the analysis. Okay, so this is the same setup as we saw, or as you will see, in the Pearson correlation matrix. Now, if we look at this correlation matrix, we see that the highest correlation coefficient is negative 0.599. Okay, so you have an inverse relationship between total mastery and total perceived stress. Basically, this means that as total mastery scores increase, total perceived stress scores decrease. Okay, now you know how to perform and interpret a Spearman rank order correlation. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to create scatter plots in SPSS. In this demonstration, I will use a data file called the 1991 U.S. General Social Survey. You can find it in the SPSS sample data folder. For this tutorial, I will create a scatter plot using occupational prestige scores and educational level. Occupational prestige scores reflect the level of social status and income associated with a person's job. So a doctor would have a high occupational prestige score, while a street sweeper would have a low occupational prestige score. The higher the education level, the more education the person has. So the first step would be to go to Graphs, then Legacy, then down to Scatter Dot, then Simple Scatter, and then Define. So then the first thing that we do is we take our first continuous variable and move it to the y-axis. So we're going to take occupational prestige scores and move them to the y-axis. And then our second continuous variable is education level, and we're going to move that over to the x-axis. Now, if we want to add titles to our charts, we can do that here, but we're not going to do that. And make sure this is on exclude cases, and everything else we really don't need. Now, if you wanted to separate the scatter plots into categorical groups, let's say for gender, right? And you wanted to have one scatter plot for males and one scatter plot for females, you would put the gender variable sex in either the row or the column box under panel. Now, if you wanted your charts to be on top of one another, then you would put them in the box labeled row. You'd move the sex variable into the row box. If you wanted your scatter plots to be side by side, then you would move the sex variable into the columns box. But we're not going to do that in this example. So then finally, we click OK. So when we look at the chart, we see that we have educational level along the bottom axis, the x-axis, and as you move from left to right, you have increasing level of education. Along the y-axis, you have occupational prestige scores, where from the bottom to the top, you have increasing occupational prestige scores. When we look at the scatter plot, we see that the plots form a shape from the bottom left to the top right of the box. This indicates that respondents with lower prestige scores also have lower education, and those with higher prestige scores tend to have higher levels of education. Now, if we run a quick bivariate correlation with education level and occupational prestige scores, two-tailed, we see that there is a significant correlation between level of education and occupational prestige score, a very positive linear relationship. Now, if we go back to our chart, our scatter plot, so then now what we'll do is we'll see what the relationship looks like if we use age instead of education level. Or let's see what the graphical relationship is between prestige scores and age. Is it that people who are older have higher prestige scores or not? So let's hit OK. Now we see here that this is just sort of a blob. There's no clear indication of whether it's increasing or decreasing. It's just just this blob. So let's run this correlation to see what the relationship is between these two variables. So we replace education with age, and then we look at the correlation, and it tells us indeed there is no significant correlation between occupational prestige scores and age. And if we look at this, we see why. There's no change between those who have lower age and those who have higher age on occupational prestige scores, just all over the place. Okay? So now you know how to run a scatter plot in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been an SPSS video tutorial from spssvideotutor.com. Thank you for watching, and much success with SPSS.
In this clip, we will talk about variable transformations. We will transform by computing, transform by recoding into a different variable, and transform by recoding into the same variable. We will use the MathAssess dataset that is already opened. The data consists of the year in college, the gender of the student, 2 questions on attitude, and 3 questions on knowledge where there is only one correct answer. The correct answer for question 1 is 2. The correct answer for question 2 is 3. And the correct answer for question 3 is 1. Any other answer is wrong. The first thing we would like to do is score these questions, which can be done by using the compute command or the recode command. Let me show you how to use the compute command first. Go to the transform menu and click compute variable. And this opens the compute variable dialog box. We want to compute the correct answer for question 1. So let's call the target variable CQ1. CQ1 will equal 1 only under certain conditions, so select if. We do not want CQ1 to equal 1 for all cases. We only want CQ1 to equal 1 if it satisfies a condition. That condition is Q1 equals 2. And press continue. Here's our condition. CQ1 equals 1 if Q1 equals 2. Click OK. And going back to the data editor window, here is the output for this computation. You can now see CQ1 equals 1 anytime Q1 equals 2. The other cases are missing because CQ1 is not defined for them. We need to go back and define CQ1 to be 0 for all other values. So go to the transform menu and select compute variable. We need to define CQ1 to equal 0 if Q1 does not equal 2. Click continue. And this is correct, so click OK. The question asks if we want to change the existing variable. The answer is yes. We want to change all missing values to 0, so click OK. Going back to the data editor window, you can see all the missing values have become 0. This is one way to score the variable Q1. Another way is much faster. To do this, go to Transform and recode into different variables. We will recode Q1, and the variable we would like to recode into we will call RQ1. You have the option of creating a label at this time, but I will do that later. So I will select Change. Now Q1 is going into RQ1. There is no if condition in this case. I only have old and new values. If the old value of Q1 is 2, then the new value of RQ1 is 1, because 2 is the correct answer. Click Add. If Q1 is anything other than 2, I want the new value to be 0. This is done by stating all other values should be 0, and click Add. This is correct, so click Continue, and OK. And going back to the data editor window, you will see the output for RQ1 is exactly the same as CQ1, except RQ1 was obtained in 1 step, and CQ1 had to be done in 2 steps. Now let us transform the other variables. Go to Transform, recode into different variables. I do not want to use the Q1 values anymore, so click Reset. This time I am transforming Q2 into RQ2. Click Change, Old and New Values, and if the old value is 3, then the new value is 1. Add this, anything other than 3, and the new value is 0. Add this, click Continue, and OK. In the Data Editor window, we now have RQ2. Let's recode Q3. Go to Transform, recode into different variables, reset this. Q3 will go into RQ3, click Change, Old and New Values, and if the old value is 1, then the new value is also 1, since 1 is the correct answer for question 3. Add this. All other values other than 1 will become 0. Add this, click Continue, and OK. In the Data Editor window, you can now see all 3 questions have been scored. 1 represents a correct answer, and 0 represents a wrong answer. What I want to do now is compute the total score. So go to the Transform menu and select Compute Variable. Make sure this is reset, and let's call the target variable Total. Total should equal RQ1 plus RQ2 plus RQ3. But you should be aware that if there are any missing values in any of these variables, the total will display a missing value. You can find the total another way by using the sum function. Find the sum function in the scroll box below, and then add it to the box above. And then replace the question marks with RQ1, RQ2, comma, RQ3. We could also say RQ1 to RQ3. And this is because RQ1, RQ2, and RQ3 are consecutive variables. So click OK. Going back to the Data Editor window, you can see one student who got all 3 questions right, and another student who got no questions right. The next thing I would like to demonstrate is how to recode into the same variable. This is similar to recoding into different variables. Go to the Transform menu and recode into same variables. Let's select CQ1, which is the same as RQ1. There is no if condition in this case. I will be putting in old and new values. I want all of my zeros to become 5, and I want all of the 1s to become 10s. Add this, click Continue, and OK. Go back to the Data Editor window, and you will see all of my 1s have become 10s, and all of my zeros have become 5s. Now you know how to transform a variable by using compute and recode, and how to use compute to get a total of several variables.
Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to perform and interpret a Wilcoxon signed rank test. Students who have anxiety towards statistics are enrolled in an intervention program to reduce their anxiety. In this demonstration, we will examine if there is a change in self-confidence in statistics from time 1, the pre-intervention test, to time 2, the post-intervention test. The first thing that we do is we go to Analyze, Non-Parametric Test, and then click on Two Related Samples. The next thing that we do is we take the scores that represent our confidence scores at time 1 and move it into the test pairs box. So confidence 1 represents our scores at time 1, or the pretest. Confide 2 represents our scores at time 2, or the post-test after the intervention. We make sure that test Wilcoxon is checked, and then we go over to options and we check quartiles, continue, and then OK. The first thing that we see in the output file is the descriptives table. It displays the number of cases for each of the 2 time periods. It also contains the scores for the 25th, 50th, and 75th percentiles for each time period. You will use the median scores, or the scores in the 50th percentile, when writing your results. When we go to the ranks table, this gives us information about the rankings. Negative ranks represent the number of people who had lower confidence scores in time 2, or after the intervention, than in time 1. Positive ranks represent the number of people who had higher confidence scores in time 2, or the post-test, than they did in time 1, the pre-test. Okay? And then finally, ties tells us the number of people who had the same scores in time 1, the pre-test, and time 2. Okay? Now, if you ever get confused, you can just look at the footnotes down here, and it has A represents confidence time is less than confidence time 1. Okay? And B, confidence time 2 is greater than confidence time 1, and confidence time 2 equals confidence time 1. Now, finally, we go down to the test statistics box. Okay? In this box, we see the z-value and the two-tailed significance level of the z-value. If the significance level is 0.05 or less, then that means that there is a significant difference in the pre-test and post-test measures. Okay? So, said another way, there is a significant difference in the confidence levels or confidence scores between the pre and post-test. So, what we do in order to determine which one is higher and which one is lower, we go back to our descriptives table and we look at our median scores, okay? And we see that the self-confidence scores in statistics increased from time 1 to time 2, right? Because the median is 20 and time 2 is 21, okay? So said another way, students had higher self-confidence in statistics after the intervention than before the intervention. Now you know how to perform and interpret a Wilcoxon signed ring test. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS. Welcome to this video tutorial from SPSSvideotutor.com. I'm Jacob Mays, and today I'm going to demonstrate how to calculate z-scores in SPSS. Okay, so in this example, we are going to convert scores on the test anxiety measure to z-scores. All right, so the first thing that we do is we go to Analyze, we go to Descriptive Statistics, we go down to Descriptives, we move Test Anxiety into the Variables box, and then we check Save Standardized Values as Variables. What this is going to do is it is going to convert the individual raw scores in the test anxiety measure into z-scores, and it's going to save those z-scores into your data file as a new variable. Okay, so then we click OK, and we see that we have a mean of 53.1458, standard deviation of 29.20, and a minimum of 8 and a maximum of 99. Now, if we open our data file and go all the way to the bottom, we see that we have a new variable called z-test anxiety. Okay, and this essentially is the z-score of test anxiety. Now, if you open up your data view and you go all the way to the end, then you will see the z-test anxiety at the very end, and those are all of your z-scores that have been calculated based on the raw scores of your test anxiety measures. Okay? Now you know how to calculate z-scores in SPSS. If you have any questions, please submit them to jacob@spssvideotutor.com. This has been a video tutorial from SPSSvideotutor.com. Thank you for watching and much success with SPSS.